Okay, so what we're going to do is we're going to build a transfer function. Where does it start here? Actually, I guess like the first slide here was just titled transfer functions. And so so a transfer function is a mathematical if I can spell, mathematical function that describes the output response of a system based on an input. All right, and so a lot of times, I guess I didn't put a block diagram in here. Let me just pop over here for a minute and try and draw this. So the idea here is I have some system. So this is my system, whether it's the guy in the bungee jumping or whatever. And so we're going to apply some input to this system and look at or measure or simulate the output. Okay, so this inside here is this dynamic system. Okay, and so we could write this as we did there as like x double dot is equal to, minus some value, I'll just call it a, times x dot minus some value b times x plus a forcing function, which I'll just call u. Okay, now these are actually all, this is a second derivative, so it's like dx dt, and this is dx dt minus bx, and x, x is a function of time. It's a dynamic system, so x is a function of time. And then my u is a function of time. All right. And so what we want to see here is we've got our x of, or our u of t is our input. Okay, so this u of t here is our input. And then our output is simply x. So our output here is x, and our input is u. So this is kind of what we're doing. We're forcing, this is our forcing function. We're forcing this, and this is our system. Okay, so the system, actually, honestly, this much is the system, and then the u is what we're forcing it with. So what we can do, the transfer function then, the transfer function is really normally written in terms of h of s, okay, which is basically defined as the output divided by the input. All right, but the s represents the frequency of the system. So, technically the system is time dependent. But the s, what we do is we're going to apply what they call the Laplace Transform. And so if you've had differential equations, you've probably studied the Laplace. If you haven't, you know, it's something to look forward to when you take your, after Calc 3, you'll typically take differential equations. And so, so anyhow, this transfer function is a representation of that differential equation in the frequency domain. All right, but when we start looking at how these systems behave, we have several different terms here that we use to analyze the system. So one term we have is what we call the steady state. So the steady state system is what happens after all the transients. So there's a transient time when the system first starts changing, and then there's the steady state. So like in your car, you know, when you're sitting at a red light, and then that, you know, say your initial condition, you're not moving, you're sitting there, the red light turns green, you step on the gas pedal, and I'm not saying floor it, but you know, you kind of step on the gas pedal, and as far down as you press the gas pedal, you hold it there constantly. So that's giving you what we would call the step response. So it's a constant feed, you know, so the accelerator is depressed the same amount. You're not changing it. And then the question is, how fast the car is going to speed up. And as the car speeds up, if you don't change the accelerator, sooner or later it's going to hit its maximum speed. All right, assuming you're going flat, you know, you're on a flat road, and you were sitting at a red light, and you know, you can go for miles and miles on perfectly flat ground. When you step on that throttle, you're going to speed up, you're going to accelerate up to a point, and then at that point you're just going to stay at that speed. And so that that speed that you stay at, after the speed quits changing, you quit accelerating, and it settles down to that terminal velocity, if you want to call it that, that it would be the steady state value, so that the system is no longer accelerating or decelerating. All right, so that's the steady state value. All right, so to measure how long that takes, we want to analyze the transient system. So the transient piece is the part where you are accelerating or decelerating until you reach that steady state point. So the steady state point is reached when that's what they call the settling time. So you reach the steady state once the system gets to where it may still be bouncing around. So like if you look at this system here, right, this is still bouncing around. And so this has not reached its steady state value, but it'll reach the steady state value when it gets within 10% of its final value. All right, so that's what we call the settling time. So the settling time occurs when the system, even though the system may be bouncing around here, over here to the right, let me get my arrow here. So, all right, so the system here is bouncing around a little bit, but it's within this frame, so it's within plus or minus 10% of this final value. That's what we call that's where you have to cut it off somewhere, because when you look at this graph, right, this thing goes on and on and on. And if I rerun the simulation, so if I come back to my editor, right, and I increase my simulation time to 110 or something, this thing is still bouncing around. You see how much it's bouncing around there? And so what we want to do, we got to pick a point. So the point that we pick is when once it gets within plus or minus 10% of the final value, we're going to call it good. Okay. Even though it may bounce around for days, as long as it stays within that plus or minus 10%, we'll be happy. And so those are just some terms. So I guess one of the big things this week is we just have some new terms to talk about. So we also have threshold points of 10%. Well, there's that 10% of the final value, or 90%. Those are those thresholds there. All right. But we also have something called the rise time. And the rise time occurs starting over here. Once you see, like, it's kind of hard sometimes to decide where to start it. So what we've done is we've just arbitrarily said, hey, once it gets up above 10% of the final value, that's our marker. When it crosses that 10% line, that's when we start measuring time. And we're going to measure time all the way here until we get over to here and stay within 10%. And that gives us our rise time. So the rise time is the time it takes for it to go between 10% to 90% of the final settling value. Okay, so but it's got to, just when it crosses 90% the very first time, it may come back down and bounce around quite a bit. So the rise time is defined as when it first crosses these 2 points. And then we also have something called the maximum overshoot. So the maximum overshoot is the maximum value minus the final value divided by the final value, and it's a percentage. So you multiply it by 100%. Okay, so like I say, we have to initialize the system. So we have to like start the system. So to start the system, we kind of talked about these last week. You could hit it with what we call a delta, which by default, delta is a pulse occurring at t equals 0. You could push it with a step response, which is what I was talking about. Like if you're sitting there at the red light in your car, and then as soon as the light turns green, you step on the pedal and push the pedal down so far, and then keep it there so you don't move it. That would be a step response. If you move it, now you're sort of bouncing back and forth. If you lit up on the pedal and you're adjusting it, so then you might a sine wave would be like a nice smooth push it down and relax it in a nice smooth sine function way. If you could do that, it'd be real hard for us to really do that. But for a simulation, it's really easy to push the system with a nice easy sine function. All right, so but we got to push the system. So when we look at our transfer function, okay, this here, what I'm showing you is the transfer function. So this here is the transfer function, and again, the S represents the derivative. Okay, so what we're looking at here is this is a third order system. It's actually got 3 derivatives. So that third derivative is like the derivative of acceleration. So it's how fast the acceleration is changing. All right, and so what we can do, we can rewrite this in the time domain. All right, so here's my transfer function. And I can rewrite this in the time domain by basically cross multiplying here, and so I can cross multiply, which gives me d cubed x. Well, actually, let me just cross multiply. So I get s cubed times x plus 6s squared times x plus 2 times s times x, or x of s, sorry, is equal to this function. I don't know why I used f here. This should have been a u most likely. This should be a u. But it's going to be like 5 times s times u. These s's should be lowercase. Okay, so we have u of s plus 3 times u of s. All right, and so all I did was cross multiply. Now, everywhere that we have an s, these are derivatives. Now, let me just zoom in here and try to make them superscripts, right? So these should be like, all right, this should be s cubed, and this one here is s squared. All right, so now anywhere we see s is a derivative. So s is effectively equivalent to saying s is equal to dx dt. Okay, for the x terms, or if it's for the u term, it would be du dt. So then if we come over here, then I can rewrite this in the time domain as being d to the third x of t dt plus 6s squared x of t plus 2s x of t is equal to 5 du dt plus 3 u of t. All right. Now, this highest order term here, again, this is a cubic, and this is a squared, s squared term here. And so this so really what we want to do now is we want to solve for this. This is our high order derivative. So again, it's like the change in acceleration because it's a third order system. Okay. And so we're just going to rewrite this. Let me actually just copy them, I guess. All right. So we're going to have this is equal to this term here, if I can get it. Okay, so I'm putting this term over here. When I do that, then, of course, it now needs to become a negative sign. So there needs to be a negative sign here. And then the next term is going to have a negative over there. And then, of course, we're just going to have a plus sign and add it to our u function here. And these values are just tagged on there. Okay. So this now, this here is our derivative. And so now all we have to do is just integrate like we always integrate. So we can just say then that, you know, dx2 is equal to dx2 of k, if you want, right, is equal to dx2 of k minus 1 plus a time step, times d3x. Okay, which, you know, what I'm doing is I'm saying that this bit right here is d3x. Okay, so this here is my d3x, and so on. So these are the same thing. And so, and of course there's a k minus 1 piece going in there. And then we can say that d then of k, we just integrate now. We're just simply integrating. Dx of k minus 1 plus our time step times dx2 of k minus 1. And then, of course, our final one is simply x of k is equal to x of k minus 1 plus our time step times dx of k minus 1. Okay, so if you're given a transfer function, given a transfer function here, you just cross multiply, and the s's are derivative terms. So if you have s cubed, then that's a third order derivative. Okay. By the way, I guess if this is s cubed here, then I guess I need the t should have had that s cubed piece there too. So, you know, this should be, the t piece should be cubed over here also. And the same with the square. So if you had this square term, yeah, it's kind of hard to get a hold of them if they're too small. Where was, let's see, this one here. All right, so anyhow, so that those terms are in there. But so, see, this is exact same thing that we've been doing here for weeks now. So there's really nothing new here. The only new thing is the fact that we started off with a transfer function. So the question was, how do we get to this from the transfer function? And again, it's just cross multiply. You just cross multiply, and the s's give you the order of derivatives. So s cubed is the third derivative, s squared is the second derivative, and just s is the first derivative. And if there's no s, then it's just your variable. Okay. So these transfer functions are effectively a differential equation, a time-based differential equation converted using what's called the Laplace transform. Now, I'm just going to give you the lowdown, quick and dirty of the Laplace transform. When you take differential equations, they'll go through the whole theory for you. But this is what I declare as the quick transform. And this quick approximation assumes that the system is at rest. So the system is not moving. So it's just sitting there, right? Your car is sitting there, the keys turned off, the system is not moving. It's just at rest. And so what you do is basically you take your first derivative and you just make that an S, and then you use a capital X when you're in the S domain. I actually underlined it here just to help highlight it, but it's not actually a vector. Okay, so I probably shouldn't have underlined those, but I just wanted to highlight them. All right, and so, but these should be capital. So what you're doing is you're changing the xt in the time domain to a capital S in the frequency domain. So you're actually going to the frequency domain. All right, and so Laplace was a French mathematician back in, I forget, it was 17 or 1800s, and he came up with this technique to solve differential equations. And so, in general, this assumes that it's a linear system. So, you know, like that chaotic system we did last week, you can't really do a Laplace on. Laplace only applies, I mean, there are some modified ones that you can work with, but basically the standard Laplace assumes that you have a linear system. So it doesn't have like an x squared term in it. All right, so, but anyhow, so that's the transfer function, and it's really easy to go back and forth between the two as long as your initial conditions are zero. If you have non-zero initial conditions, it's not hard, but there's an extra piece in there that I pretty much am ignoring because I'm assuming the system's at rest, which is typically what we do when we're trying to analyze these systems. All right, so if you want to integrate this, you have to, just like we've always been doing, you set your time step, you build your t vector, and you initialize your values. And then here, because we're going to have a forcing function, so you're going to have your forcing function. So this is a step response of unity. So it's just one forever. All right. So it's just one forever. And then you have your then you have your for loop. So you evaluate your acceleration term or your derivative term, and then you integrate. So these two here are just simply integrating. Okay, so the two in blue there are just your integrators. And so if you have a third order system, then you're going to have 3 integrations. If you have a fourth order system, then you're going to have 4 integrators. But really the system doesn't change. All right, now the thing is though, if we have a transfer function, all right, so in this example here, here's my transfer function. I have 1 divided by s squared plus 1s plus 5. So this is my transfer function. Matlab and Octave both have the ability for you to just type this in. So what you would do is your numerator doesn't have any s terms. So if you wanted to, you could match it. So you could put like 0, 0, 1, where these are your S terms, but it's best just to leave those off. And then for the denominator, we're just putting the coefficients 1, 1, and 5. All right. And so you build a variable called your numerator, which are the coefficients in your numerator. Then you build a variable for your denominator, which are the coefficients in the denominator. And then you call the TF function. So you say my transfer function, h of s, which I just, you can't use parentheses or subscripts in the Matlab code, so you just call it h of s, is equal to the trans function of numerator comma denominator, and it will pump out a system. So I can just do that right here. So I can come over here and I can say my numerator is 1, my denominator is 1, 1, 5. And then you have to have the package installed. So there's a package command. And for this to work, and I've got pretty much everything installed here, but for this to work, you have to have the control toolbox installed. All right. So you have to have that installed, and you have to have it loaded. So you can do package, load, control. And so now if you list it, notice it'll have a star across that shows that it's been loaded. Okay. So you have to have the package installed, and then you have to load the control package. And you can just probably list the one if you want, just list control. Because I was just messing around. I installed practically every package they have for Octave here. But all right, so we have our numerator and our denominator. And now I can create my transfer function, h of s is equal to TF numerator comma denominator. And they're going to print it out. Notice how they printed this out. Just like it shows over here, right? 1 divided by s squared plus 1 over s plus 5. So it prints it out just like that. And then we can create our time step. And we can create our time vector. And I have no idea how to run this, so I'm going to run it for 5 seconds and see what happens, and then we can adjust it. And now I can say y is equal to step h of s comma t. And, well, I should have put a semicolon there. And now I can plot t comma y and look at my step response. And there's my step response. The thing is, I didn't clear my figure. Okay, so if we look at it again, there's my step response. Now the step response is still bouncing around. It hasn't settled out. So I got to recall my t, and I'm going to run it for 15 seconds and see if that's any better. Okay, again, I should probably clear my figure. And I need to recalculate. This is why we do it in M files, so you can just have it done. So here you can see, now this was too long, so I ran it for 15 seconds. I probably should have ran it for about 12 seconds. So I'll try it one more time here. So I'm going to run t to 12 and recreate my y and then plot it again. All right, so there is a nice step response to a second order system. And the system is, 1 divided by s squared plus 1s plus 5, which is a transfer function. All right, so again, this is basically like a bungee jump here. What you're looking at, when we look at this transfer function, so if we take this here transfer function, okay, this term here is your acceleration, right? S squared is your second derivative, that's acceleration. And this term here is your friction. So this term here is the friction, and this term here is your position term. All right, and so basically we have the, okay, this term here is also known as omega squared, where omega is the natural frequency of the system. All right, so 5 is omega squared. So if you take the square root, that'll give you the frequency of oscillations. Now, omega, the units of omega are in radians per second. So let me just kind of write omega here. So omega is in radians per second. So remember that radians are 2 pi, so the frequency is omega divided by 2 pi. Let me draw a pi symbol here. So, okay, so the frequency omega is radians per second. It's how fast it's actually oscillating around. And so the frequency in hertz, which is kind of a linear definition of the frequency, you divide by 2 pi to get that linear aspect of it, or the radius, effectively, of that oscillation.